Okay, I think we can start. Is there anything else before starting? Right. So you all can hear me, right? One. Okay. So today I want to introduce graph theory to especially people who have not seen graph theory before. If you have seen it, the first 15 to 30 minutes might be a little, things you've seen before. In that case, I've sent the handout and there are plenty of hard questions at the bottom, and you can always try those, right? These questions, and there are a few easy questions if you're not comfortable, and I will come to some of these questions, and I'm hoping I can do those in due time, right? Also, again, if anybody has any question, just stop me, right? So first of all, I must tell you that graph theory is an active field of research. It's actually notoriously simple to understand the basics, right? I think its difficulty is a little overrated, but the point stands out. It's extremely interesting. There are lots of things you can do with it, but the structure of the subject itself is very simple. So, and we're only going to concentrate on graph theory in the case of olympiad mathematics, and because there are a lot of things you can do otherwise, right? So some of you might be confused as to what graphs really are. So I mean, you the graphs we are talking about are not those, the functions, f of x versus x, y, whatever functions. They're not the x-axis, y versus y-axis type of graphs. They're actually, it's not even related, right? um it's sad that two different things have the exact same name, but we will have to make do with that, right? But these are completely different, and these are structures, right? So, and what are these structures? Well, you basically have some vertices, and you have some edges connecting a few vertices, right? Maybe it can be all of the vertices being connected, or maybe it can be some of them, right? It can be of any sort, right? And that's it. That's what a graph is. It's a bunch of vertices, and some pairs of vertices are connected by edges, right? And almost always, like as far as I can remember, we only talk about finite graphs, which means that the number of vertices and hence the number of edges are both finite, right? So I hope you understood what I'm saying so far. It might be a little vague, and it should just make sense as we go on, right?
All right, sir.
um so, and there are a few things we can do with these. So one thing is that in general, right, in the most general thing, you can have multiple edges between the same vertex, right? You can have, like, I don't know, multiple edges between two vertices. But most of the times we ask for that not to happen, right? We say you can only have at most one edge between two vertices. So if that is the case, then we call it a simple graph, right? If we can have at most one edge between two vertices, we call it a simple graph, and we will be dealing almost fully only with simple graphs, right? There is another idea where actually can you just like mute your mic, right? Yeah, like if there's something, you can put it in the chat, right? So right, so the the other idea is, instead of simply connecting two vertices with edges, you can put an arrow to it, right? So instead of just saying these two vertices, some two vertices, this vertex and this vertex are connected by an edge, you can give the edge direction and say this way, right? Something like, or this, right? So you can give all the edges a direction, and such a graph is called a directed graph, right? So one way to interpret such a thing, one interpretation could be, say these four are teams in playing in a tournament, and whoever is winning has the arrow pointed towards them, right? So maybe this team has only played once but have won their match, and you know this team has won their one match against this team, and this team has won their two of their matches against these two but lost against this team. So you can see the interpretation, right? On the other hand, just to be complete, an interpretation for a normal graph, that is one that is not directed, could be like, two people handshaking. So you say that any two people who have shake their hands are connected by an edge, right? And for example, this person has only shake their hands with one person, while this person has shake their hands with every other person. Right? So that's that. One last obvious, somewhat natural generalization is, instead of letting an edge connect only two vertices, you can actually say let an edge connect multiple vertices, and this is called a multi-graph, right? But we won't be talking about those, and they don't get involved in olympiads. We will be talking about directed graphs though, and mostly we'll be keeping our graph simple, right? So moving on to moving on. So a path.
One question, sir. Sir, can you please give a example of an infinite graph? I have not seen any picture of an infinite graph.
Sure.
So, in
Pankaj,
case,
Pankaj, a small request. Can you write down any question in the chat?
yeah, yeah, yeah.
Right. So just to
Okay,
be
okay.
complete, an infinite graph is, it just has infinite vertices. There's no example as such. It just has infinite vertices, and you can connect them anyhow you want, right? I mean, an infinite graph is one with infinite vertices. That's all, and you can connect them with how many ever edges you want. Something like that. I don't know. you know oh wait, I should have used different colors. I'll just do that. I'm sorry about that. Right, so you see this graph, it has, I believe, six vertices and multiple edges, right? So let's look at some things. So a path is basically, it's exactly what you mean, right? So a path could be something like this. So this is a path. A path is a series of vertices which are all connected to each other, right? It's basically traveling along some vertices to get from somewhere to somewhere. So that's a path, right? We will be looking at, maybe special types of paths, etc. And you right. So, and you can also notice that two vertices are supposed to be, we call them adjacent, incident, or connected if there is an edge between them, right? So most of the terminology here actually quite makes sense, right? It makes perfect sense. um a complete graph kn, so the n means that there are n vertices. Say for example k4 has um four vertices, and all four vertices are connected to each other. So this is k4, right? Kn is a graph with n vertices all connected to each other. That's what called the complete graph. On the other hand, if we do have a complete graph but which is directed, that is where every edge has a direction, right? We call that a tournament. And I hope you see the reason why. The reason is that, um, in a normal tournament, say you have a tournament with 10 teams, and we have all 10 teams playing with each other. Then that's what it would look like, right? So for example, a tournament could be this. I'll just add arrows to this. It's I'm sorry for the untidiness, but that's a tournament, right? So where this team basically won every match they played. This team sorry, this team won every match they played, this team lost every match they played, etc. So a tournament, to repeat, is a complete directed graph, right? So the don't worry if you don't remember these. You can always look them back, look whenever you're whenever it's convenient for you, and in a due time you'll understand, you will remember. Right. So a graph is called. I'm just going through a definition, so we can go through more on stuff. Correct. Aryan is correct. Right. I could have asked that question. A kn has n choose two edges, right? N into n minus one by two edges. Oh, wait, is it n into n plus? I think it's n into n plus one by two edges, right? Kn will have n into n plus one by two edges. Um. Oh, sorry. I'm confused. I'm sorry. N into n minus one by two. I'm really sorry. I'm really sorry. Wow. Right. Okay. So a graph is said to be, again, a graph is said to be connected if any two vertices can be linked to each other through some path. It's exactly again, this is exactly what it means to be, right? So if there is a vertex which is not connected to anything else in the graph, then it's disconnected. And if there's a bunch of vertices over here which is not connected in any relation to something, it's called that. These are, if they're all part of the same graph, this is a disconnected graph, because this not connected to this in any way. So that's what connected means. And if you find a subset of the vertices which are all connected to each other, right? So let's say you find four vertices somewhere, right? This might not be obvious. I'm not that great at drawing. If say there are four vertices like this, and all four are connected to each other, right? Then those four points form a clique, right? Basically those four vertices with their edges connecting them form a complete graph, and that's called a clique, right? So a clique is not that important of a definition, don't worry about it. And our last definition before we go ahead is the definition of degree, right? Now, this might not be obvious, I don't know. So you could, if you have not seen this before, you should just listen a little, I guess. So in a graph, the degree is the number of edges, right, coming out or connected to a certain vertex, right? A degree is only defined for a vertex, and the degree is the number of edges. For example, the degree of this vertex in this three-member graph is 2, because it has two edges, right? It's somewhat obvious, I think, right? So if you have, so for instance, the degree of this vertex is 3, the degree of this one is 2, and the degree of this is 1, 1, and 1, right? If there is something here, here, and here, right? And as such, a natural extension to directed graphs is that out degree and in degree. So out degree is the degree going out. So for example, the out degree for this vertex is going to be 1, and the in degree is also going to be 1, because there's one arrow coming in and one arrow going out, right? So for the out degree of this is going to be 0, and the in degree is going to be 1, right? So I think all these should be rather natural. To this, let's just try a few questions, I think. So yeah, just before going on, you need to know that in graph theory, the number of edges starting from a vertex is its degree. Correct, Rudra? That's correct. The number of edges starting from a vertex is its degree. The number of arrows going out in a directed graph of for a certain vertex is its out degree, and the number of arrows coming in is its in degree. And as I said, degree is something defined only for one vertex, right? You talk about a degree for a certain vertex, right? Right. So Connectedness, right? So connectedness is just that, um if if you have two sets of vertices. So yeah, if you want the definition, a graph is said to be connected if you can go from any one vertex to another vertex through a path, right? So that's the definition. If that's not possible, if you can't reach from some vertex to some other vertex, it's not connected, right? I don't think we'll actually need that definition in any case, but it's good to know. Right, so the first problem here is this called the handshake lemma, right? Basically it says that the sum of degrees in any graph is the sum of degrees is twice the number of edges, okay? And this is somewhat obvious, it's a simple double counting argument. So because for each of these edges, for say this edge, for this edge, right, we are counting this edge twice. Once when we are counting the degree from this, because the degree is counting the number of edges, right? And once when we're counting from this, right? So for every edge we're counting the we're adding to the sum, right? For every edge we're adding to the sum twice. So the sum of degrees is equal to twice the number of edges, right? Right, every correct, Aryan. Every edge contributes 2 to the degree, and hence this is 2. So I hope you can see this. If not, you should draw something and write down the contribution of each edge until you get this. Um, on a very similar argument, you can get the second one, right? Which is basically saying the sum of out degrees is equal to sum of in degrees equal to edges. Because every edge contributes 1 to the sum of out degrees and 1 to the sum of in degrees, right? Respectively from the vertex it's going out of and the vertex it's going in. As a matter of fact, if this is not clear, these things are actually not required, right? For the going on, and if this is not clear to you, like you should try it out now, right? Just see, write down some small cases and try to prove this. The third one is a little more manipulative. It says in a tournament, remember? So in a tournament, all the vertices are connected in some direction, and there's either up there's it's connected in some fashion, right? um as a matter of fact, so how do you do this? You'll notice that in a tournament, for any vertex v, the out degree plus in degree equals n, right? The n minus 1, I'm sorry, n minus 1, where n minus 1 is the n is the number of vertices. If there are n vertices, then the out degree plus the in degree is n minus 1. um I hope this is obvious, because but it's basically a connected graph, right? So if you're connected to every edge using either a going out arrow or a going in arrow, then all the going out arrows will be counted in the out degree, and all the coming in arrows will be counted in the in degree. And all of these must be counted together, and you have exactly n minus 1 edges, right? Because it's connected to all the rest of the n minus 1 vertices. So the out degree plus the in degree is the n minus 1. And at this point, the solution is just substituting this, substitute the out degree as the n minus 1 minus the in degree into this place, and simplify, right? It'll work out. And I'll leave that to you, right? So I think I didn't complete this point I was trying to say before. In graph theory, right, however hard the questions, induction, you should always try induction, right? Induction is something that more often than not works. It might not be direct, but graph theory is like, it's like meant for induction, because it's not that much, as I might be exaggerating, but it's always worth a try. And the reason for this is because if you remove um a vertex or a edge from a graph, it still remains a graph, right? It retains the structure of being a graph. right? What I said might be a little vague, but that's the reason induction works well, right? Because you can still apply the same principles most of the time, at least. So one question to try this, like, just to get comfortable with induction, is this is example 2. So it says that every tournament has a directed um Hamiltonian path, right? Right. You can usually add a vertex and prove, or remove a vertex and prove. More often than not, I think we usually have a graph given to us, so we remove a vertex. Many times we remove an edge, but usually you're actually it's not that direct. You're supposed to be a little smart about the induction, right? Like, or else it'll become obvious, I think. I don't know, but you have to be a little smart with the induction. But you should always be on the lookout for induction when solving a graph theory problem. Anyway, um so Hamiltonian path, right, is a special type of path. In example 1, statement 3, is it the sum of degree in degrees squared? Yes, the in degrees are squared and then added up, right? The in degrees are squared and then added up, right? So every tournament has a Hamiltonian path. Is a special type of path, and it's a path that goes through every vertex exactly once, right? It goes through every vertex exactly once. You can't go twice, and you need to go through every vertex exactly once. In a connected graph, the Hamiltonian path is obvious, like obviously possible. Like in a normal one, not a directed one, you can just go from 1 to 2. If you label the vertices 1 to n, you can just go from 1 to 2, and then 2 to 3, and then 3 to 4, and so on. In Yeah, needless to say, in a directed graph, a path can only go in one direction, right? You need to follow the arrow. You can't go opposite the arrow. That's the very definition. And this example claims that every tournament that is a complete directed graph will have a Hamiltonian path, right? That is, there will oops that there will be a series of vertices, right? You can use using edges that go through every vertex exactly once, right? And note that it doesn't need to come back, right? So, and like, I'm just gonna explain the solution. Like, it might, I don't know, it might be a little, if you are seeing graph theory for the first time, this might be challenging. But no, it's not obvious, Aryan, because we're talking about a directed graph, right? So you may not always be it's not always possible to go from one vertex to another if it's pointing in the opposite direction. And right, so this might not be a trivial question, but I just gave this example here to give you a feel for how induction might be done. So it's just so I think I can let you do the base case by yourself. The base case is somewhat obvious, right? You can do it for two vertices or three vertices, I think. And yeah, arrow might be in the opposite direction, so it's not obvious, but it is true. um so the base case for the induction is obvious, that is. And I hope everybody knows induction, right? That's somewhat of a prerequisite, I hope. Right. So let's assume this to be true for n minus 1 vertices, right? Let's assume this is true for n minus 1 vertices. And we have a path then, right? And then let's try to prove it for n vertices. Given it's true for n minus 1, let's prove it for n vertices, right? So we have a bunch of you know um vertices, and let's say these are the n minus 1 vertices, and this is the nth vertex. The actual geometric position of the vertices doesn't matter, right? This is just a visualization tool. A graph is only a visualization tool. And except when you're talking about planar graphs and planarity in general, it doesn't actually matter, right? Where you put the things, you just need to connect them, right? Right, so let's assume it's true for n minus 1. Th- this means that in these n minus 1 vertices, I've not drawn the edges, right? That would become difficult to do. But there's an arrow between every one of these vertices. This is the nth vertex, right? So we assume that it is true for n minus 1, right? So that means that we have some form of a that goes through every vertex, right? This is a Hamilton path. It goes through every vertex exactly once. And this is what we are saying. We are assuming that this is true, right? All right. So now looking at this, we realize that we only need to, we've assumed for n minus 1, and we're trying to show that assuming for n minus 1, n is true, right? That's what induction does. And now we need to add this vertex in the path somehow, right? We need to add this vertex in the path somehow. So let's see. Wishful thinking tells us that if this arrow exists, then we're done, right? We're basically done. Um, so let's assume otherwise, right? Because if that's there, then we're done with the question. So let's assume that this arrow is in this direction and not x, right? So let's assume it's in this direction. Now, what if this um you don't need to explicitly give the construction. We're not explicitly giving the construction. I'm just trying to think out loud how we might go forward with this. So on the other hand, if this edge existed, right? If from this the new vertex to this one, then we're also done, because then we can simply make this the new vertex the starting point, right? Swap the vertices. Arjun, can you just explain what you mean? Why? Right. If it's not clear, we're just trying to introduce this new vertex into the into this path, right? And if we're just I'm just saying that consider graph with a new vertex and leave the first one. No, a Hamilton path needs to have all the vertices, right? It needs to have all the vertices. So I need to reduce this. So if this vertex, if this right, so if this one exists, right, then we're done, because then we can make this the starting point. Yeah, we can use IH for what's IH, right? And we can make this the starting point of the Hamilton path, and then we're done. So we're gonna basically have to assume the contrary. That is, we're gonna have to assume that x the, the new vertex, it's in this direction, the edge is in this direction, um right? So now you can see, I hopefully you can see the dilemma, right? That now we're like, you can see where we're going with this, right? The thing is that we want to add it somewhere in the middle, and adding it somewhere in the middle is possible if from one of these vertices, say vertex 1, and say we have vertex 3, and this is the vertex we need to add. At any point, say this part of these two vertices are somewhere in the middle. um we want something like this, right? And why will this be true? Look, let's call these the vertices 1, 2, 3, 4, so on till n minus 1, and call this n. Since there is an edge that goes from 1 to n, if there is an edge that goes from n to 2, we can simply insert n in between 1 and 2. So we have to assume that the edge goes from 2 to n, because otherwise we can insert it there. And similar thinking says that an edge has to go from 3 to n, because otherwise if the edge goes on the other direction, we can insert n between 2 and 3, right? And we can continue this till the end, till say n minus 2. And we can say that even in n minus 2, we need this edge, right? If this is to be false, we need this edge to go from this n minus 2 vertex to the nth vertex. And but we know that we do again need the edge to go from n to n minus 1, right? So somewhere then so we can then anyway add the nth vertex between the n minus 1 and n minus 2, and then we're done, right? Now I know I might have explained this really bad, but I hope you understood the idea of what we're doing, right? We're simply assuming in n minus 1 vertices that we have a graph, that we have a Hamilton path, and we're using it, right? We're using it to go further. So you can try it again later on your own. Looking into example 3, you can do that on your own. You can research what a Hamilton um sorry, what an Euler circuit is, right? So now we get to some more interesting stuff. So a cycle is a path, it's exactly what you think it is. Cycle is a path that starts and ends at the same point, or it's never ending, whatever, right? So cycles are, of course, as you might know, very important in olympiad graph theory, and in general, right? It's an important pattern. So look at this question. It says that if the minimum degree is d, then there is a cycle of size d plus 1, right? And how do you do this? I'm just gonna solve this question for you. So the idea is that if the minimum degree is d, so assume the longest path, right? This is more or less of a greedy algorithm. So say assume the longest path is some n long, right? Wait, I don't understand why we can't have all the edges go out into vertex n. Why? Oh, Avan, if in that question Eeks, I raised those things, but even the last vertex, right, the n minus 1th vertex goes out to the nth vertex, then we can add the nth vertex at the end of the path, right? And if all the vertex, oh sorry, and if all of them come into the thing, if the nth vertex comes into the first vertex, then you can add it into the beginning, right? Is the degree of vertex? Yes, I'm talking. If the it's oh right. Just to clarify, example 4 says that all the vertices have degree at least d, right? They have at least d edges coming out of them, right? And they're saying there is a cycle of size d plus 1. And to prove this, I'm just going to state the proof, right? I hope you'll get a better intuitive understanding of how some graph theoretic proofs can be made. Just assume the longest path of length is n, right? Then the fact states that, then the idea is there that you need this vertex, say this vertex, to be connected, definitely to be connected to each and every one of these vertices. Why is that true? Because if that is not the case, then there is, by definition, another vertex that you can go. But this is not possible because we assume this to be the longest possible path, right? We assume this to be the longest possible path, which means that for this vertex, right? For this vertex, all edges connect to the vertices in the path itself, which means it has to connect to this vertex, this vertex, this vertex. And since the minimum degree of this vertex is d, there are d of this plus 1 of this. And of course, it'll be connected to the first vertex as well. So it'll be a cycle of size d plus 1. Now, this might look like cheating. This might, the argument itself might feel like cheating. I don't know. But just look at it once more on your own. We just, it's somewhat of a simple proof, but the main point, right, the main gist of the proof is assuming that like taking the longest possible path and using that, right? And this is a general principle, to be honest. When you're stuck in a question, especially in combinatorics, but in other fields as well, when you're stuck, get something, make something up, however silly, right? Get something concrete to make with, right? Your progress won't be perfect, it won't always be inspired, right? Make something silly and work with it. Always have something concrete in your hand, right? What does it mean by size of cycle? The size of cycle is the number of vertices in the cycle, or the number of edges. Yeah, the number of edges or the number of vertices, right? That'll be the same, right? Just look at it. The number of vertices and the number of um, edges will be the same in a cycle, and that's the size of the cycle. Okay, so I hope you all understood this specific example, and let's move on to what a bipartite graph is, right? So a bipartite graph is again an important one. So a bipartite graph is a graph in which we can, right? We can split the vertices into two groups, say blue and red, such that all the edges go between these groups, right? There are no two blue vertices connected, and there are no two red vertices connected, right, to each other, and the only edges run from blue to red, right? Of course, you won't actually get a bipartite graph in practice. Not all bipartite graphs are represented, with one group to this side and one group to the other side, right? But the general principle holds. In other words, you can color the vertices red and blue such that no two red or no two blue uh, are connected, right? The two vertices must be different. I don't get what you mean by that, Rudra. So just as a general example, often as a non-example really, this graph, a triangle, to be honest, triangle to be specific, is not bipartite, because even if you color one of these blue and the other one red, there's nothing to color this with, right? So I hope you understood what this means. Okay, a very important thing, right, is a graph is bipartite implies that it has no odd cycles. That is, there are no cycles of odd size, right? It's an if and only if. I'll come to the other part, and I think this must be obvious, because if there is if there is a cycle, let's say you start at a red vertex, right? Then you have to go to a blue vertex, and then you have to go to a red vertex, and then you have to go to a blue vertex, and so on. And if there is a cycle, you have to come back. But if you're coming back, you can only come back from a blue vertex. So if you keep count, of the first red vertex is, say, is 1, you're flipping red and blue every time. So there is bound to be an even number of vertices or edges in any cycle, right? So I hope you can see this, right? If this is not clear, look again. A graph is bipartite means that there cannot be any odd cycles. Surprisingly enough, even the converse is true. That is, if a graph does not have any odd cycles, then it is bipartite. And the proof is, to be honest, not that difficult. It's just a logical argument saying, suppose a contradiction that the graph, it has odd cycles and the graph is bipartite. But if a graph is bipartite, you can't have any odd cycles, right? If there is an odd length by PHP, there will be vertices which share an edge, right? Right. Thereby is telling the correct thing, right? If there is an odd cycles, then if you color those red and blue alternatively, you can't do that. At some point you'll have two colors of the same vertices adjacent to each other. As for Avin's question, I'm sorry if I'm pronouncing your name wrong. Can we split the vertices into three groups? In general, you can split it into k groups. It won't be called bipartite, but you call it k partite, right? You call it k partite, right? Right. So the third thing here is we actually I we okay, yeah, the next section is trees, and that ought to be interesting, right? So a complement of a graph, right? Again a definition. So let's say you have a bunch of vertices with some edges. The complement of a graph is a graph. It's basically you copy the same vertices, right? These are the same vertices, except you connect an edge exactly where there isn't any, right? So I hope you can see it's basically in some sense the complete graph minus the graph is the complement, right? So you connect edges where there aren't any, right? Was this clear? For example, in this in this one, this vertex is it, this edge and this edge aren't connected. So here we connect those two. On the other hand, in this graph, these two vertices are connected by an edge, so they are not connected here. So if this is G, this is G complement, right? These don't appear that much as well. The only reason I am telling you is I intend to solve a question that uses this later. But anyway, it's nice to know this is what a complement is. And the last definition for this section is um like set complement. Somewhat, yes. It's the set complement of the set of edges. But I think the intuitive definition, it's better to actually understand what it is, right? So as I've written here, a lot of questions in graphs can be made on coloring, right? On coloring both, you can color the edges, in this somewhat like bipartite, and in generalization of k-partite, that's related to the coloring of vertices, right? You can also color edges, right? And you can make many questions on by setting many different types of conditions on these colorings, etc. And there's actually a lot in graph theory that I won't be going through, even olympiad graph theory. But again, I want to do a question on one of these things later. So just to give a definition, the chromatic number x of the graph is the least number of colors that you need to color all the vertices, right? You're assigning a color for each vertices, and this is the least number of colors. So such that any two colors are not connected. Like two vertices that are connected do not have the same color, right? I hope you understood what I'm saying. If that is for okay, can you guys tell me what the x is for a bipartite graph? Anybody? That's correct, right? 2 is the answer, right? You can always as I said before, you can always color a bipartite graph with two colors. You can connect it with more, but you need at least two. You can't do with one most of the time, right? In general, a k-partite graph has chromatic number k, but you usually don't know, right, if it's k-partite. That's the actually the definition, right? If chromatic number is k, then you call it k-partite. That could be called a definition. In any case, you can try example 6. You need to prove that if the maximum degree of a graph is d, then the chromatic number is at most d plus 1, right? Yeah, so you can use an algorithm for this, right? So what you do is take any vertex, give it a color, right? Then move on to all its neighboring vertices, and Prabnu, no, it's not mandatory to have at least one edge, right? But I don't really remember an instance where a graph with only vertices is actually useful. But yeah, in any case, no, it's not necessary. Yeah, in any case, coming back to the question, if the maximum degree is d, then you should show that the chromatic number is at most d plus 1. And the way to do this is that is in the way to do this is that, select a vertex, give it any color. Then since all the there are at most d neighboring vertices, and since you have only used one color so far, you have at least d colors. You can definitely assign all the vertices with some color or the other, right? Even if they're all connected to each other. So I hope you understood the proof for this, right? Of this statement. And equality occurs in the case of a complete graph, right? That is, you will notice that this is true in the case of a complete graph. The chromatic number of a complete graph is n, right? And you know obviously that as I said before, that the maximum degree of a chromatic graph is n minus 1, right? Yeah, it is possible to color the graph with one color. That means there are no edges, right? So yeah, that's true. Correct. What Debayu said is correct. This works because you will have at least one color remaining for the other vertex. If Because you have, the fact is that if you have d plus one colors to use, you have many colors, right? You will always have some colors left, even if you start coloring randomly. So that's the idea for example 6, right? So does anybody have any questions? I'll move on to trees. Any questions? So what is the equality part? Oh, I just said that in I the claim was that if the maximum degree is d, then the chromatic number is at most d plus 1, right? And I'm claiming that this is true. That is, the chromatic number is actually equal to d plus 1 in the case of a complete graph, right? A complete graph is the one where everything is connected to each other, and in that case the maximum degree is n minus 1, right? The maximum degree is n minus 1 because every vertex is connected to all the n minus 1 other vertices. And the chromatic number of a complete graph is n. Can everybody see this? The chromatic number of a complete graph, kn, is n, right? Because you need n colors because everything is connected to everything. So in the case of a complete graph, if the maximum degree is n minus 1, the chromatic number is actually n, right? It's d plus 1. So we will be coming to trees at this point. So trees are graphs that look like, wait, give me a second. This, right? I don't know, something like that. Um, can an edge have, no, an edge has to connect two vertices. Please explain example 6 briefly. Oh, I just said that, you can use an algorithm where you can, just randomly color the vertices until you're done. And you can always color vertices, right? Um, Ramnu, correct. There can be loops, but we are talking about simple graphs, right? So we are assuming there are no loops, right? A simple graph means that there are no loops and there can only be at most one edge between two vertices, right? So a tree looks like this, but what it actually is, right? Intuitively, it is a graph without a cycle, right? And it's basically a graph without a cycle and as many edges as possible. Like, if you start filling in as many edges as possible for a given set of vertices, at some point you will be forced to have a cycle, and we will make this formal later. But the idea is that if you have as many edges as possible and no cycle, you get what is called a tree, right? And as it happens, this as many edges happens to be the number of vertices minus 1, right? You can count here in this, the number of vertices is 1 plus the number of edges, right? You can look at this graph and count the one, and you can draw many trees on your own. The only condition is that there should be no cycle. As a matter of fact, if you look at example 7, I'm actually not going to prove this, but it's very important that you try it on your own. if the graph is connected, right? If the graph is connected, that is everything is connected to everything else, right? And you can go from one to another place and there are no cycles, that becomes a tree, right? In general, as you can look in example 7, this is true, that any two of these three imply the other, and this is a really useful lemma, right? This example 7 is really useful, and is very worth experimenting with, right? So again, the idea is that if you add one edge to a tree, then you create a cycle, right? If you add one vertex to a tree, you create a cycle, right? It doesn't matter where, you will create a cycle. If you add any edge to a tree, sorry, any edge to a tree, you will create a cycle, right? um and I talked about trees in two different aspects, right? One is the leftmost thing where I gave the definition of what it is and the properties and such, and the rightmost I made it look like this. And I haven't actually shown that trees actually look like this. And how you can do that is by proving that there will always be a vertex of degree 1. So to do that, you can assume contradiction and say that if this is false, then all the vertices have degree greater than or equal to 2. And using this, you can show that if all the vertices of are have degree greater than or equal to 2, then there will be a cycle, right? There has to be a cycle, and I'll let you do that. So if you count the fact that there has to be a degree 1 vertex, right, and then you say you delete it. Now you'll notice that the fact is that if you delete a vertex and its corresponding edge, right, a degree 1 vertex and its corresponding edge, then you'll notice that T is still connected and T will still have no cycles. By deleting a degree 1 vertex, you can't make the rest of the graph unconnected, and you can't remove cycles by delete. You can't add cycles by deleting a vertex, of course, which introduces the idea that there are by deleting a vertex, by deleting a degree 1 vertex, it still remains a tree, right? The graph still remains a tree, and this should reek of induction, right? This means that induction in turn works very well with these kind of things, because you can delete vertices and do this. So it's like if we delete a root of a tree, it still remains as if it is, right? Right. It doesn't remain as it is, but if you do delete, it's called a leaf, by the way. A degree 1 vertex is called a leaf, and if you delete the leaf, the graph still remains a tree, right? Root is vertex. What? I don't know what you mean by Pankaj. A degree 1 vertex is called a leaf, right? That's just trivia. In any case, you'll also notice that a graph has to be sorry about that, a tree has to be bipartite. A tree is always bipartite, and this is something you can remember as well. And the proof, it comes directly from, I believe, example 5. A tree has no cycles in the first place, let alone odd cycles. So that means that a tree is bipartite. So you know j- just directly, can anybody tell me what the chromatic number for a tree is? 2, right? The chromatic number for a tree is 2, because it's bipartite, and the chromatic number for a bipartite graph is always 2. um okay, so just hearing this out, a very important idea is that a tree is the maximal graph, right, without a cycle, and that if you add a edge, it introduces cycle, as I said. This means that, and this very important, I'm sorry about that, a t has n minus 1 edges, right? So this is an important fact. So this means that if you have n edges, then it is likely to have a cycle, right? And how we prove this is through example 9. But before we get there, I need you to understand that There are many graph theory questions in which you are asked to prove that a cycle exists of some sort, right? Hopefully, if we have time, we'll be doing a question. Oh boy, time is running out. And in general, it's a very useful idea to look at a tree in those cases, right? It's very useful to look at a tree in those cases, because a tree means that if you get a tree of some sort, that means that if you add one edge, you get a cycle, right? So the best idea to actually prove that there is a cycle, a good idea in fact, is to take a subset of edges such that it becomes a tree, and then add in an edge, and then you show that it has to be a there has to be a cycle. And that's pretty much the proof for example 8. That's exactly what we're going to do for example 8. um but for that we need example 9, right? And we're going to have to introduce the idea of a spanning tree. Now, a spanning tree is a subset of the edges. It's the graph that you get by deleting a few edges. And to be specific, we're talking about a spanning tree for a graph, right? We're talking about the spanning tree for a graph is a subset of edges such that the resulting graph, right? If you delete the few edges which are not there, the resulting graph is a tree, right? Not in a tree. A spanning tree is a subset of any graph, right? A spanning tree is a property of any graph, and it's a subset that states that the resultant is a tree. So basically all the vertices will be connected and there will be no cycle, right? And example 9 asserts that every connected graph will have a spanning tree. Now this is non-trivial and an important fact, right? Basically what this says is that um a connect you can delete a few edges in any connected graph, and the resultant will be a tree, right? The resultant one will be a tree. Can you give an example of a spanning tree, right? Something like that, right? So take those and take this thing and say we are trying to find the spanning tree of this graph, right? What Pankaj said is correct. And say this is a tree. So the ones I colored black form a tree, right? That forms a tree. All right. So that is one spanning tree, right? Spanning trees are not unique, but what I'm asserting is that in any connected graph, spanning trees do exist. Okay, so I hope does I think my explanation for trees was a little bit vague and had some holes. So if anybody has any confusion or any questions at all, I want to know now, right? So we're gonna move on to questions after this. We'll solve some Olympiad questions. So just put it in the chat if you have questions of any sort. No tree was natural. Okay. I don't know what that means. Right. So yeah, so to prove example 8, how you prove example 8? Take a graph, take its spanning tree, right? Now the spanning tree will have exactly n minus 1 edges, right? The spanning tree will have n minus 1 edges. And now if you take in any new vertex, right? If it has n vertices, if it has n or more edges, there is at least one edge which is not there in the spanning tree already, because in the spanning tree there are only n minus 1 edges. So this means that since you're adding an edge to a tree, you will result in making a cycle, right? There will result in making a cycle. So I hope you all understood example 8. Example 8, 9 and 7 are all very important. you know they help you a lot. As a matter of fact, we're going to use this idea in example 10. I think the example 10 came in the Olympiad called the PUMAC. Um, I think I put this in the example set for the other class, I think. So anyway, um, I think I'll give you a couple of minutes to try this. I'll explain the questions in the minimum time. Yeah. Um, so what this says is that you take a graph, right? You take a graph, maybe one here. You take a graph, right? It can have cycles. It can do whatever, and you're allowed to do this. You're allowed to pick a cycle in the graph. Say this one, right? Let's call the cycle C. You can introduce a new vertex. Then you can go on to delete. Oops, oopsies. I'm gonna have to do that again. Right. So there you go. Something like that. Right, something like that. And say you can pick any cycle. Say you're picking this one, and you're introducing a new vertex. Then you're gonna delete these three edges, the cycle that you have selected, and you're gonna replace them, those three edges, by three new edges. Right? I hope you all are trying it in the meantime. So you have to prove that this process eventually stops. Right? Now you cannot say, as would be natural, that the number of cycles reduces. This is not true, because say for instance you have a cycle, something like that, something like that, and you take this, you delete this and this, and you introduce a new vertex connecting these, then you will notice that you actually have more cycles here if you look at this carefully. um so the point is that if you try a few examples, you'll notice that the number of cycles may not reduce as you may want, right? Then you would want the very natural solution would be to show that the number of cycles is a monovariant. The number of cycles in this process reduces. So I hope everybody has read the question and understood it. So this question has given us a process where they've given us, they're saying that you're adding a vertex, you're doing something, right? And they're asking to show that we'll eventually have to stop. And I actually don't want to explain this question fully, but I just want to give you a certain, expose you to certain ideas. We'll practice other questions. So the way we do the solution for this question is basically by introducing a monovariant, right? A monovariant is a quantity that only increases or decreases, and this is a pretty intuitive one, right? The idea is that if you look at the number of vertices and the number of edges, right? um do we have to do it? You can do it if you want. If you look at the number of vertices and number of edges, yes, this session is recorded. If you look at the number of vertices and edges, the number of edges, you'll notice, this is a critical observation, remains the same, right? I hope all of you can see this, because if you take, say, a four-member cycle, if you take a four-member cycle, then you're introducing a new vertex and adding what? Give me a sec. You're introducing an edge to each of these, right? You're introducing the edge to each of these. So the thing is that the number of edges will remain the same. We have to delete only three. I don't know what you mean. But the number of vertices, since you're introducing a new vertex, increases by one. And the endpoint is that at some point, if you keep increasing vertices, the number of vertices and the number of edges will remain equal, will get equal, And that is when example 8 proves gets in. If you have an equal number of vertices and edges, then there is a cycle, right? If you have an equal number of vertices and edges, there is a cycle. And if you increase beyond that, right? So this is somewhat of an idea, right? There are many details to be taken care of. And this is a monovariant that you must use, right? Because you will notice that if you increase one more after this, then you will get n. Say if you have n vertices and you'll have n minus 1 vertex edges, right? That doesn't mean you have a tree, but that does mean something. So you know what, I'm gonna let you solve this henceforth. But the main idea was noticing the fact that this gives you the handle for the number of vertices and the number, a correlation between the number of vertices and the number of edges, right? So you can try example 10 later and try to formalize it. Of course, stating the idea for a question is one thing, and actually figuring the details out is another. So you can always post the solution, or you can ask for hints on the Discord, right? So let's start solving questions right now. Example level 11 is a somewhat of an easy one, and it basically is, if you read it out, it states that all the vertices have degree 2, and they're saying, and the main goal of the question is to see, like, you want to characterize how all graphs look like. If all of the vertices have degree 2, how will the graph look like? And the answer is that it has to be in a cycle like this, right? There has to be a collection of cycles like this. Okay, and you can prove this formally, but it's somewhat intuitive, right? The only possible graphs, it can all be in one cycle, or it can be in hundreds in a, like 10 cycles or whatever. The only possible way for all the vertices to have a degree 2, exactly degree 2, is in cycles like this. And if you have a cycle, it's obvious, right? You should be able to select half of the vertices. You should be able to select half of the vertices, right? So you can try that out again. That's the idea. It's almost a direct question, but it introduces another important idea in olympiads. um Wait, I forgot what I was going to say. uh yeah, right. So instead of proving the goal into which I was trying to prove, that is, instead of directly trying to prove that no two of them are played each other, I was trying to go for something more general, right? I was trying to characterize all such graphs. I was trying to see how all such graphs actually look like. So this is common, right? So often it's harder to find out exactly what you're going for, and often you need to actually prove something more general, and the ideas will come out directly from that thing, right? So that's something you'll often have to do, and don't shy away from doing that. Don't shy away from conjecturing that something more general than the statement they have given is true. Anyway, in an olympiad you mostly will have a lot of time, so that trying shouldn't be an issue. So that example 11 is done. Example 12, there are um there are 1,000 cities in the country of Caledonia, Uliria. Oh my goodness, why did I say Caledonia? Uliria, and some pairs are linked by dirt roads. So graph theory problems are very thinly disguised. You'll get directed graph questions mostly in the form of tournaments and people speaking. On the other hand, you'll get many graph theory normal graph questions on cities and roads connecting them, right? So the example 12 here says that you have 1,000 cities and some pairs are connected by dirt roads. That means you have a bunch of vertices. And how many minutes are left? 1 hour. So what? Oh, the class ends at 8:30, by the way. Right. So you have a bunch of vertices which represent the cities, and then you have a bunch of dirt roads connecting them. Randomly prove that the government of Uliria can pave some of the roads so that every city will have an odd number of paved roads coming out of it. So this is a very good application for spanning trees, right? I hope you can all see how you can do this. The idea is that, since we're given a connected graph get from any city to any of these roads, basically means that the graph is connected. So what do you do for this question? Just take a spanning tree. Actually, as a matter of fact, this is already a spanning tree. But just take a spanning weeks. Yeah. So take a spanning tree. So now you have to delete that vertex. You can delete that vertex which I just wrote down. But yeah, so that's the thing. So if you take okay, so what are you gonna do with the spanning tree? Right? So it says that we need every road to have an odd number of roads coming in or out of it. So this means that I mean, we don't know how to proceed, because in a tree you can have something like this, right? And say this vertex has degree 2. So in specific, what I'm trying to say is that it's not exactly necessary for it's not exactly necessary for in a spanning tree to for all the vertices to have odd degree. But what you can do is select the leaves, right? So select, say, this leaf. It's wishful thinking, right? So we know that if we take this leaf and select, say, these both, and only have the paved row between these both, then we are done, right? Because um like we are done with between these two edge vertices. And you might think that induction is possible tool, right? So what I mean is that you might think of deleting these two cities and then going forward. But that unfortunately is not possible, because deleting a vertex might remove the connectedness condition which is required to make a spanning tree. So instead, you just need to notice one thing, that if you have a spanning tree, right? If you have a spanning tree, you need to select all the edges connected to the to the leaves, right? Because if you don't select them, then the leaves will have no road coming out of them, and that's zero, right? So you need to select every possible edge coming out of a leaf. So I hope you all understood that. And on second thoughts, you might think that taking a spanning tree and choosing edges out of this might not be that good of a strategy, right? That maybe it's possible that it might not work in a spanning tree, but it has to work otherwise. So actually, the thing is that if you think a little, you'll notice that it has to work for a spanning tree also, because a spanning tree is again another distribution of edges. And the fact is that it has to work for the spanning tree, right? Because if the spanning tree was the set of edges given to you in the beginning, then it should have worked. Then the question statement is asserting that this is true for that as well, as right. This is a subtle point. What I'm trying to say is that by actually removing all edges and making your graph a spanning tree, you're not losing out on anything. You're not losing out on anything, because the question statement guarantees us that it has to be possible for a spanning tree, right? So basically, we're making our life simpler, and now we can actually use the fact that our graph is a tree. Now, how we're gonna do this, how we're actually gonna solve this question is slightly algorithmic. Oop. Um, right? It's slightly algorithmic, and what we're gonna do is, take take a graph, take a tree like this, or right, and so let's start selecting all the edges we think are necessary. We need to select this edge, this edge, this edge, this edge, this edge, this edge, and this edge. Oh wait, this edge and this edge. We need to select all these edges, as I said before, because they're connected to leaves, right? And say for instance, if you don't select this one, then the degree of this vertex, and after you pave all the roads, will be 0, which is even. So you need to select all these, right? Now start somewhat at the bottom. Say start over here, right? So now you will notice that this edge is connected to these two, and now the degree of this is even, and we need to make this odd. So we will have to select this as well. We have to, right? Now you'll notice that the degree of this, what, I think that I only split everything into two, which is a bad idea, to be honest. It's possible to do this, right? Yeah, so anyway, so we have all the necessary ones selected. I'm really sorry for being untidy. So you will notice that again, in this, if you look at this vertex, then it has an even degree so far, so we have to select this, right? On the other hand of things, this vertex already has an odd degree. So this blue vertex necessarily has to be paved, and we will not select it. And so we do this again, right? So we start from here. We have to select this. We have to select this. We should not select this. And we should not select this, right? So this is an algorithm we'll do, and you'll notice that by construction, we're actually almost done at this point, but you'll notice that by construction, um, all the vertices except one vertex, that is the last one to be used, have to have an odd degree, as we want, right? It has an odd number of paved roads, so it has to have an odd degree, has, except that last one, right? And I will leave it to you, and it's not a very simple task to prove that the last one will also have an odd degree, if automatically, because the number of cities is even. You need to make use of the fact that the number of cities is even, and if you use this, you will get the fact that the last one will automatically have an odd number of things, right? So that's example 12. And again, you can, if you don't get this last part of the proof, as I left it to you, do tell, and I'll put it there. So all these questions are much harder, and looking as I only have 10 minutes, I won't be able to solve, of course, most of them. So I want to solve the 18th one, and if I have time, the 19th one. So okay, so what, and this question is the reason I introduced the chromatic number and the complement. So what the question is saying is that if you have a graph and its complement, it's asking for all such possible graphs, say on 4 vertices in this case, what is the maximum possible number and minimum possible number? There are two different questions of the chromatic number of this plus the chromatic number of this graph. What is the maximum possible number? For example, the chromatic number, um, why graph theoretic terms? And you know what? Actually, in many of the questions, the original questions were not actually given in the terms of the graph theoretic things, but it's actually very shallow, right? You can easily convert it into a graph theory question. It's almost very thinly disguised, roads and whatnot. If you look at you look at example 19, you have airports and airlines between them. it's very easily disguised. Anyway, so you'll notice that the chromatic number of this graph is 2, because you can connect this with RG, right? It's I didn't actually include that because I included questions which I thought was somewhat nice, right? Anyway, and the chromatic number of this is 2 as well. So the sum is 4. So how do we solve this question? As a matter of fact, I wanted to do this a little more detailed, but this is a long question, and we're running out of time. This is the last question we'll be solving anyway. So let's do the minimum first. We have 10 minutes. I think that will suffice. So for the minimum, right? And the 100 vertices is seemingly random, right? We can, we can replace 100 by anything else, and we're gonna take smaller cases. So what we're gonna do in this case, what we're gonna do in the case of 100 vertices, in the case of the minimum, I mean, is we're gonna make a very important observation, right? So let's say you have a certain graph like this, and you color it with the minimum number of colors. And in this case, since you have a triangle, it's not bipartite, so you need at least 3 colors, and you can color it with 3 colors, right? You can make this and this red, that you can leave that one blue, and you can keep this green. So you need 3 colors, so the chromatic number is 3. On the other hand, the complement will look like this, this, it'll look like that. Am I missing anything? 4 plus 4, 8. For the minimum, can we not select any edge and get a chromatic? No, 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 you cannot select an edge. You're given the graph and you're given the thing. You're given the graph with all its edges, and you're given the complement, and you're summing the chromatic number of the graph and its complement. And we're asking, over all such graphs, what's the minimum, right? We can get and if you select a graph which does have a chromatic number of 1, then you will notice that yes, I'm doing example 18. Oh, I'm sorry if it was not obvious. I'm doing example 18, right? So you'll notice one that by selecting a graph with a very little chromatic number, you're basically reducing the number of edges, which means that in the complement, the number of edges will be very high, which will increase the chromatic number there. And we're looking for the minimum of the sum of the chromatic numbers, so we need to be careful about this balancing act. Okay, hope you understood what I meant. The chromatic number of this one is 2 though. Okay, right? The chromatic number of this is 2. Now what we're going to notice is that Eeks. Right. What you might notice is that um you can connect here. You might as well, right, add an edge between 2 vertices of different colors. So you can say add this edge, right? And this won't change the chromatic number because it's still proper. On the other hand, this will cause the deleting, right? And notice that I'm actually giving you a process, right? I'm using a process, right? I'm talking about a general result, right? I'm actually using only 4 numbers. So this will delete this edge over here, right? That edge I just deleted. So this is actually doing is that if we're adding an edge in the main graph, let this be the main graph and this the complement. We adding mm, if we're adding an edge in the main graph such that the chromatic number doesn't decrease, uh, then you'll notice that the chromatic number of this graph will remain the same. On the other hand, the chromatic of the number of this graph may remain the same, but it can also decrease, right? It won't increase because you're deleting an edge, right? If you're going to start deleting edges, the chromatic number cannot increase, it can only decrease. So inspired by this, let's take it to the full ending point, right? If the chromatic number of your given graph is, say, some k, basically connect all edges which are of different colors. Just do it, right? And this will anyway in the main graph, and consequently in the complement, since stuff will start disappearing, the chromatic number may or may not disappear. And let's actually look at how it's going to look at the end, right? If we do this process, what's going to happen in the end? And as you may have guessed, in the end we're going to get a k-partite graph, but it's something more than a k-partite graph, because if you have, say, if you put all the different colors to different sides like that, the main graph is gonna look like the main graph is gonna look like ew, right? The main graph is gonna look like, if you're connecting all blue to all green to all red, right? You can't obviously connect them inside each other, but you just connect them all, right? Whatever. You connect them all, right? And the thing is that the chromatic number will still stay 3 at the end. So the chromatic number stays the same, and this is what you get, right? Notice that there's no harm in doing this process, because with by doing this process on any graph, you are at least reducing or the sum, right? This xg plus xg complement that we actually want to minimize is reducing or remaining the same. So it follows that any graph which is the minimum has to be of this shape, has to be of this size, right? Because if assume a contradiction, if this is not true, then you can perform this algorithm on any graph, and then you'll get a graph of this type which has a less or equal to, right? And that's a contradiction if you just got what I'm saying. So we only need to look at graphs of this kind, where you have a bunch of vertices where if two vertices are in a different bunch, they will be connected. In any case, let's see what G complement looks like. So in G complement will look like this, right? Basically, all the different pools of graphs will all be connected to each other, right? And now we want to minimize this. And can anybody tell me what the the chromatic number of this graph will actually be? Like, one possible doubt, this is all the prerequisites for GT, and now we have to work on problems. Mostly yes, these are almost all the prerequisites. There are a few things I've written here which you can learn further, especially that things like Hall's marriage lemma and stuff on bipartite. There's also some Turan's theorem and other stuff in extremal graph theory, Ramsey theory and stuff like that, which you can all learn, but these are the prerequisites. Yes. So the answer to this question is that the chromatic number, you see, you'll notice that all of these graphs, if you can see that this is the complement, right? These two are complements of each other. And I seriously think that this problem is hard to understand. So please later, just revise what I said and try to go over this problem again. So in any case, the idea is that since every vertex here is connected to each other, if they're not in the same group, the complement will look like this, where every vertex inside the same group are connected to each other, but outside they're not, right? So the chromatic number of this complement will be the maximum of the chromatic number of all these disjoint portions. I hope you can see why, right? So because you can use, say, red and blue here, you can reuse the same colors red and blue here, but you need a third color, green. So the idea is that the chromatic number of this graph, right, G complement, will be the maximum of all these, and the chromatic number of any of these, right? Since say here we have four vertices, say you have four, then you'll have a four all you'll have four vertices all connected to each other in the complement, right? I might be getting ahead of yourself, but at least try to vaguely understand what I'm trying to say. So what you get is a four clique here, and the chromatic number of this will be 4, the chromatic number of this is 3 and 2, and so the chromatic number of the entire graph as a whole will be 4. So what I'm saying is that the chromatic number of this G complement will be the size of the maximum clique, right? And the chromatic number of G itself, the chromatic number of G itself will be, K, the number of these things. Um, so you know what? I'll give the maximum to do to you. I'll just do the minimum, and we'll leave it at that. So let's say we have K colors. Let's say the chromatic number is K, and then you'll notice that if you have K of these, the maximum size, let's say if you have 4 groups and 10 vertices, then the maximum size of any of these by pigeonhole is 10 by 4, right? So it's just a simple calculation. You can't have 12 because you only have 10 vertices. So I hope you understood what I just said. If you have K vertices, sorry, if you have K groups, then the maximum number of vertices in one group is 100 by K ceiling. Because if it's more than that, then you can multiply K into 100 by K. You can let all of them be the size, and this will give a contradiction because then the number of vertices will be more than 100. And as we said, the chromatic number of this graph is at most 100 by K as well, because the chromatic number is the size of the maximum clique, right? It's size of the maximum group. Here the answer is 4. So we are trying to minimize K plus 100 by K. K is the chromatic number of G, and 100 by K is the X of the G complement, right? And you can solve this by AMGM, right? This by 2 is greater than or equal to 100 root of 100, and you'll notice that the answer is 20. So 20 is the answer, and how we can get it is by splitting by the way we did it, split the graph into 10 groups of 10 vertices each and connect them all to each other, right? And you'll notice that the answer is then 20. So that's how you do the minimum. And I understand that I think I sped up a little too much by the end, right? I'm I might have given a very steep incline, but I hope you got some exposure to how graph theory problems work in olympiads, and you can try these questions, right? I think you should be able to do that. um just as thing, if you understood even the basics of today, especially only the first section, tomorrow's class will be on a very special application in graph theory. Atman will be taking it. And the idea is something called, you come there, even I'm not sure on that actually. Even I'm gonna attend because I don't actually know what the stuff he's gonna talk about. um but I don't think it's that difficult, right? So if you understood the basics, you should be able to get here. Anyway, I understand that I might have gone too fast in the end, and so if you have any questions at any time, please message me. You can try some of these. You can try example 13, it's another easy question, and you can try some of these harder questions as well, and you can ask for hints in the Discord. So other than that, if you don't have any questions, you can leave, I guess. And if you have any questions, you can ask right now.